Hello everyone. In this video, we are going to understand how does GRPO work. GRPO is the reinforcement learning algorithm which is used to prepare the model DeepSeek. Now, GRPO is an algorithm which builds upon years of research in the reinforcement learning field, and in this video I'm going to condense everything down so that you understand how GRPO works from scratch. We'll start with classical reinforcement learning and slowly we'll build our intuition to understand why GRPO was so effective and why it became so popular after it was introduced by DeepSeek, and why it remains one of the most popular algorithm for building reasoning large language models. Let's get started. So, in a typical reinforcement learning problem, we have an agent and we have an environment. The agent interacts with the environment. Typical notations which are used in classical reinforcement learning are that of states, actions, and rewards. The agent is in a specific state. Imagine a Roomba robot going around the room trying to clean your room. And depending on the state in which the agent is going to perform certain actions and going to get rewards from the environment. Now, what are these actions? If you consider the Roomba robot, the actions can be movement in the room or going back to the charging station and recharging. And what are the rewards? Well, let's say we give the robot a reward of negative 100 if the battery discharges while moving in the room. At all other times, let's say the reward is 0, and when the robot collects some trash, then we give it a positive reward. These are states, actions, and rewards. You can represent any reinforcement learning problem as a function of these three variables. And they are quite intuitive as well. If I am playing a chess game or I am teaching an agent to play a chess game, then the state is the current configuration of the pieces on the chessboard. The action is the movement of the pieces on the chessboard, and the reward is negative 1 if I lose the game. If I win the game, the reward is positive 1. So these are the states, actions, and rewards for an agent as described in a typical agent environment interface. Now, the main question is that what happens if we apply reinforcement learning to large language models? What would be the states, actions, and the rewards? Well, firstly, in large language models, the agent is the LLM itself, which is either a DeepSeek, a GPT, a Llama, etc. And the agent is the LLM, and the environment with which it interacts, it's either a Python interpreter or it's a data set or they are humans. But essentially, the environment is something which gives you the answer uh, after you type in the prompt. So the LLM is taking some action and you're seeing something on the screen. And in between, what happens is carried out by the environment. It is kind of fuzzy, but just stay with me right now. It will become clearer as we go along. Let's start to understand what are states and what are actions. Let's take a simple example. Imagine that we have a prompt which says Roger has 5 tennis balls and he buys 2 more cans of tennis balls. Each can has 3 tennis balls each. How many tennis balls does Roger have now? We know that the answer is 5 plus 2 into 3, that is 11 tennis balls. Now let's try to understand what are the states and the actions in this case. The first initial state which my LLM receives is simply the prompt itself. Now, given the prompt, my LLM is taking the first action and giving me the first token which says Roger. Now, this Roger is passed back to the environment, and now the next state is my initial prompt plus Roger. Now, this state is passed as an input to my LLM, and then it takes the next action, which is has. You see what's going on here. So, for every single iteration, I get my previous state as an input to the new state plus the previous action as an input to the new state. So my first state is just prompt, then I have S0 comma Roger, then I have S1 comma has, then I have S2 comma 11, and then I have S3 comma tennis. So whatever is being output by the LLM is passed in the state space for the agent, and at every single iteration I'm performing an action. The first action is Roger, the second is has 11 tennis balls. So this completes my answer, and I finally get Roger has 11 tennis balls. These are the states and actions which we have when we represent large language models as agent environment interface, typical to classical reinforcement learning problem depictions. Now, this is how the states and the actions are represented. What about the rewards? Remember that after these initial 1, 2, 3, and 4 iterations, I am not getting any reward. I am only getting reward when the entire answer completion is over, which is in this last iteration, when my LLMs takes the action as balls and I get a reward. If this answer is correct, then my reward is 1. If the answer is wrong, then I get a reward of 0. So if the answer is 11 here, I get a reward of 1, otherwise I get a reward of 0. So this is very unique to large language models. In traditional reinforcement learning problems, we get rewards after every action, and uh, this we see in all kinds of RL problems. But in large language models, for a longest time, you do not have any reward, but only when the answer completion is over, you get a reward. And then that becomes the reward which is applied to the entire answer, which is kind of strange and unique as well. So, for all these initial iterations, the reward is 0, 0, 0, 0, 0. And then finally, you get a reward of 0 or 1, depending on whether the answer is correct or the answer is wrong. So this is how you can represent a large language models in the format of an agent environment interface. So what happens is that you get the first token, take an action, then combine the previous token with the action, you get the next state, take an action, combine the previous state and the current action, you get the next token, etc. You continue the process till you reach the end of the answer, at which you will get a reward. So this is how it happens. There are a series of states and actions, and finally you get a reward. Now, the question is, if the reward is positive, then I have to, trace back through this entire chain and update my LLM. And if the reward is negative, I again have to trace back through this entire chain and update my LLM, which is quite a journey, right? Because sometimes your answers can be very long. And the major challenge here is, how do we make these updates to your large language models? By focusing on the rewards? How do you change the parameters of your large language models such that they take the feedback which you are getting from the rewards itself? So let's start to look at that in detail. So imagine that you have the state which says S0 comma Roger, where S0 is the prompt, and your LLM has taken the first action and given you the token Roger, and now this is passed as a state to your LLM. Now, what the large language model is doing is that it's trying to understand what would the next best possible word be. And to understand that, it takes in all the words in the vocabulary or in the dictionary, and it calculates a word probability distribution for all these words, and it finds out the word which has the highest probability of occurrence. So here you see that the highest probability for the next word is being given to the word has, and the least probability is being given to the word have. So this means that my model is telling me that the next best possible token for whatever state you have given me is has. So then what I will do is, my model will choose the action A2, and then it will be passed through to the Python interpreter, which is the environment we are assuming. Now, let's say the action is taken, but we do not know whether the reward is positive or the reward is negative. If the reward which we receive at the end of the sentence completion is positive, then what we do is we go back to this probability distribution which my model has generated, and we want the LLM to in, increase the probability for has and decrease the probability for all other words. And if the reward that I receive at the end of the sentence completion is negative, then I want my LLM to decrease the probability for the word has and slightly increase the probability for the other words. Now, intuitively, these are the updates which I expect to happen to my policy or the model uh, after I receive my rewards. And by the way, I have introduced a symbol here which is pi theta. This pi theta is called as the policy, and which is equivalent to the large language model. And it is this policy that we want to optimize. We want to optimize this policy such that if the reward is positive, I want to tweak the probability distribution in a certain way. If the reward is negative, I want to tweak the probability distribution in a certain other way. Now, this is done by policy gradient methods. Uh, and we are going to understand how these policy gradient methods work briefly. So, imagine that the policy, it actually depends on a lot of parameters, but here we have assumed that the policy only depends on two parameters, theta 1 and theta 2. And let's imagine the policy to be a smooth surface, which is shown in the diagram. And imagine that you are somewhere here in the middle of this peak, or in the slope of this mountain. You are present at the yellow dot. Okay, so we are currently standing on the yellow dot, and we are traversing a mountain which tells us the probability of taking action A2 when I am in the state S2. Now, if the reward is positive, which means that I want to reinforce my action, the action that I have taken is good because it's giving me good rewards. I want to move upwards towards the peak of this mountain so that whenever my model sees the state S2, the probability of taking action A2 increases. So I'm going to slowly and steadily move up the mountain. But if the reward is negative, then I'm going to move down the mountain. I'm going to move away from the peak because I want to penalize this action. I don't want my model to take this action when it reaches state S2. So I'm going to penalize the model and going I'm going to move away from the peak towards the base of the mountain. Now, naturally, if you want to implement this kind of an algorithm, calculating the gradient is going to be the key. And this the direction of this gradient is given by grad of theta pi theta of a2 given s2. And this is also known as the gradient of the policy, and these methods are subsequently called as policy gradient methods because they allow us to estimate the gradient of the policy so that we can take necessary steps towards the peak of this mountain or towards the base of this mountain. Now, mathematically, the policy gradient update can be represented as this, which is simply using the gradient ascent rule, where instead of simply using the derivative of pi theta, we have used the derivative of log of pi theta. And R is the reward which you collect at the end of the sentence. So we have this gradient ascent rule which we use to iteratively update the policy parameters in such a way that the final policy that we get, if this reward is positive, you can see that it's going to move up the mountain. If the reward is negative, so that information is baked into this formula very nicely. In reality, what happens is in many reinforcement learning problems, this reward is not received only at the end of the episode, but it is received after every single action is taken. So instead of the notation R, people prefer to use this notation G of t, which indicates the cumulative expected rewards which the model get from which the model gets from that state towards the end of the episode. So it is basically rt plus 1 plus rt plus 2 plus dot 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 till the final reward which the agent receives at the end of the episode. This algorithm is called reinforce. It is quite similar to the expression that we see here. The only difference is that the single reward r is replaced by the addition of all the rewards which the model or the policy receives from the state towards the end of the sentence completion or the end of the episode. Now, people also modify this slightly by subtracting it or subtracting from it a baseline function which is called as b of st. So this is called as reinforce with baseline. The reason this is done is because if you calculate all the rewards which the model receives at s1 s2 s3 s4 etc and sum up all of them, the chances of variance are huge. And that's why what you do is you subtract it from a baseline which is indicative of the value of each state, so that the rewards that you're getting at every state are almost equivalent. So it's a way to reduce the variance for the policy updates. Now, usually this baseline function people use another terminology which is called as v phi of st, which is called as the value function. Now, the value function has a very interesting intuition. It denotes the value of a particular state, which is the cumulative sum of all the rewards which the agent is expected to receive in the future, and you take the expected value of that. So imagine that we have a team, we have a sports team, and let's say there are 11 matches in the tournament, and the player has not performed well in the first two matches. Now, the coach can easily take a decision that I'm not going to have this player play the rest of the matches. But typically, what happens is that if the value of this player is high, the expectation that the addition of all the runs or the goals which the player is going to score in the remaining matches is going to be high. The initial failures don't matter because it's the expected value of the final sum that matters. So, as a coach, if I believe in the value of this player, I will allow the player to play for all the matches. That is exactly what the value function means. The value function means what is the expected value of all the cumulative returns which the model is expected to get in the future. So you have g of t, which is the single return from that state, and you subtract that with the value function for that given state. These are also called as actor-critic methods, and this difference is sometimes denoted by the advantage function called a of t. Now, how does GRPO differ from these methods? What GRPO said is, well, these formulations are good, but in language models, you only get a reward at the end. So, what is the point of adding all these rewards in the middle, which are anyway zero? So, why do you need to use another model to estimate the value function that is going to consume a lot of memory and time as well? So you get rid of all you get rid of this value function estimation part, and there is an easy way of calculating this baseline or this advantage. So the first thing they did was, this g of t was again replaced by r, which is the current reward, but the baseline was replaced by not the value function but by something else. So what is that something else? Let us see. So in the GRPO methodology, instead of, let's say, we have this first output, which is state S0 is Roger, then state S1 is Roger has, state S2 is Roger has 11, etc. Towards the end of the sentence, you allow the language model to generate more responses. Instead of one single response, you say that let the language model generate four responses or five or even 10 responses, and then you calculate all the rewards which the environment or the uh, answer completion receives at the end of the answer completion. So these rewards are called RS1, RS2, RS3, and RS4. Some of these sentences are going to be really bad, they will get low rewards. Some of these are going to be good sentences, they are going to receive high rewards. So these rewards will have a probability distribution which, or value distribution, which looks like this, where here you can see reward 1 has the maximum value, and then these other three rewards have a low value because the sentences are probably not related to the prompt, or the grammar is wrong, but the answer completion is not making sense. So then what we do is, we normalize these rewards, we subtract the mean, and then we divide all these rewards by the variance. So you get something like this. Now this is negative because it has the lowest value, and this is positive because it has the highest value. Now these are the values that you use for the advantage, and this you can then substitute in terms, in the place of 80 over here, which are the normalized rewards for all of these different answers. This makes the calculation very simple because you now do not need to calculate the value function model at all. You just need to calculate the rewards, and then once you get the rewards, you are set because you can calculate the advantages from the rewards itself. You don't need to worry about a critique model or the value function model for the purpose. And this can be written simply as r minus mean of rs divided by standard deviation of rs, which is exactly what we did in this process. We subtracted the mean and divided it by the standard deviation. So this is the policy update rule, which is written for group relative policy optimization. Now here the example which I have shown right now, all the rewards are received after the entire sentence has been completed, but there is another variation of this where the rewards are received after every thought is completed. So let's say there are five thoughts which lead to this answer. So again, there also the formula remains same, but then you have rewards given to every single thought in the chain of thought process. But we don't need to completely understand that to understand the GRPO, the essence of the GRPO algorithm. So I am choosing to not cover that in this video. So now this is the policy update rule where you have a very simple and neat way for calculating the advantages. Now, what we do is, we say that okay, this is the gradient ascent rule, this is the gradient, and from this we backtrack and we say what is the loss function. So this is the loss function because the gradient of this exactly gives you this gradient. Now we are not done here. There have been research papers post 2015 after the paper on trust region policy optimization was released, which have focused around one idea, which says that if you do not want to if you do not want the policy to deviate that much, then you have to restrict your updates. So basically, you have a region and you allow the policy changes to happen only within that region. And the reason is that usually before the reinforcement learning steps are applied to large language models, the base model is already good and you do not want to make too many changes to that base model. So you restrict the deviation of the new model from the base model. And this restriction is done by imposing a border, and you say that if this yellow dot moves beyond this border, you take it back towards the border. Basically, you do not allow your yellow dot to move towards the peak of the mountain, you restrict it in some area. You allow it to ascend, but you put a barrier to that ascent. You do not allow the policy to deviate that much. And this has worked quite well, especially in large language models when it was first introduced in the paper Trust Region Policy Optimization. Now, with this addition, our loss function is going to change, and we are going to look at how exactly does the loss function changes. So let's see. Okay, so the first line is the vanilla policy gradient loss, where we have not implemented uh, this concept of having a trust region. Now we are going to cover PPO loss for a while because GRPO is directly built on top of that. So we define a ratio R theta, which is called as the ratio is epsilon. Let's keep it at R theta. So R theta is pi theta divided by pi theta old, and you say that we will not allow this pi theta to go beyond 1 plus epsilon, and we will not allow it to go below 1 minus epsilon. So basically you clip it, and epsilon is the clipping parameter. So you apply a clip function to this, and then everything else stays the same, but you just apply a clip function, and this clip function tells that my new policy or the current policy is not going to deviate that much from the old policy. It's going to remain within bounds. If it goes beyond 1 plus epsilon times the old policy, I'm going to bring it back inside. If it goes below 1 minus epsilon times the old policy, I'm going to bring it back above. So it essentially is restricting your policy updates to uh, within that region. Now, the PPO update is not exactly this. There is a small variation to this, which I'm going to explain in the next four slides. And this variation is a little bit nuanced. So let's try to understand that. So now, first, let's look at what do we exactly want. So look at this graph. On the x-axis, we have r of theta, which is pi theta by pi theta old. And on the y-axis, we have what exactly do we want to do to this function. So now if the advantage is greater than 0, which means that the new policy is better than the old policy, and or in other words, the probability of uh, if the advantage is greater than 0, it means that whatever action I am taking in the new policy is behaving better than the default policy behavior. So I am going to allow the same ratio to continue till 1 plus epsilon, and then I'm going to clip it after 1 plus epsilon, because I do not want to make very large updates, even if the new policy is good compared to the old policy. So I clip it. Now, if the advantage is less than zero, what I do is for large R of theta, I do not clip it because, anyways, the new policy is worse than the old policy. So, even if the if the advantage is negative, even if R theta is very large, my policy is not going to deviate that much because I'll be penalizing my policy anyways. But if my R theta is less than 1, then the penalization will be very less. So I wanted to penalize uh, the new policy even for lower ratios. So even if my, let's say my pi new is very small compared to pi theta old, which means that I am somewhere close to the origin. So if I don't clip it here, then I'll be penalizing less. So I will clip it, which will ensure that even if r theta is very much less than 1, I am still clipping my rt of theta. So these two graphs are essentially ensuring that if the advantage is positive, I'll not get too much greedy. I'll not let my policy deviate that much from my old policy. If the advantage is negative, then I'm not worried if RT theta is greater than 1, because anyways it will be penalized by a large extent. But if RT theta is less than 1, I still want to penalize it. So I'll clip it below 1 minus epsilon. Now we want this. So, or it can be expressed in a single graph where the orange curve indicates the function that we want for advantage greater than 0, and the yellow curve indicates the function that we want for advantage less than 0. Now, this function which we had come up with before will only give us this. So it's basically telling us that if RT theta is less than 1, it's clipping. If RT theta is greater than 1, it's again clipping. So it's only giving us the clip function. Whereas we want something like this, we want a different behavior for advantage greater than 0 or less than 0. So how is that achieved? Well, that is achieved by taking a minimum of, you multiply that clip function by the advantage and RT theta by the advantage, and you take a minimum of that. What will that ensure? Well, just look at this. If you are uh, between 0 and 1 minus epsilon, this is 1 minus epsilon, this first vertical line. So the minimum is going to be this line, and if the advantage is greater than 0, which is exactly what you want, and if the advantage is less than 0, then the minimum is going to be the yellow line, which is again what you want. And then the middle curve is common for both, so we are not worried about that. And if rt theta is greater than 1 plus epsilon, which is over here, then if advantage is greater than 0, you have this red line, which is what we want. And if advantage is less than 0, then you have this yellow line. So multiplication of this advantage and taking a minimum of these two is giving us exactly this curve, which is what we are expecting. So all of this explanation is just to change this uh, PPO initial objective to an objective which gives us the minimum of r theta into a of t and the clip function into a of t. If we take a minimum of these two functions, we are going to get exactly the curve what we want. So there is a small tweak that we make to the previous PPO objective. And after making this small tweak, we can write our objective function for, or the loss function for GRPO as follows. We use the loss function from the PPO loss function itself, but we subtract a term which is multiplication of parameter beta and the KL divergence of pi theta and a pi reference policy. Now the KL divergence helps us understand how different is the new policy compared to the old policy. And here by PyRef, we are referring to the base model, which is the initial supervised fine tune model, after which we are again fine tuning the model using reinforcement learning. So, this is the PyRef. So, this term is making sure that the new model does not deviate that much from the base model either. So, this is how the GRPO loss function is written. Now, to summarize everything that we have covered so far, step one is once we get the state from, uh, let's say, the user types some, or let's say we have a bunch of prompts and we have a bunch of answers. So, what we do is we take those questions one by one and we feed it to the LLM. Then what the LLM does is that the LLM, which is also called as pi of theta, it takes that prompt in and it generates a probability distribution which is given here. Along with that probability distribution, it also generates multiple other outputs. It generates maybe 10 or 100 other outputs, and it calculates the rewards for all of these outputs, R1, R2, R3, R100. And then you normalize these rewards and you get the advantages which are denoted by AT. Once you get the advantages, you are in good position to calculate the loss, and this loss is given by LPPO minus beta times the KL divergence. Remember, LPPO can be calculated once we have the advantage function, and this is the KL divergence between the new policy and the reference policy, which also can be calculated. And then we apply a gradient descent update rule to update the policy parameter. So this is essentially taking care that whatever rewards my model is receiving for the answer it has given to this prompt, based on that the policy is updated. If the reward is positive, then I'll update the probability distribution accordingly. If the reward is negative, then my action will be penalized and I'll update my probability distributions accordingly. So this will be done for all the prompts and questions that we feed to the model, and it will keep on changing the model iteratively for all the questions that we have. And this is how the entire policy will be updated, so that the policy gets better and better and better using reinforcement learning and by leveraging the rewards that we get and improving the model based on these rewards. Thank you everyone. This brings me to the end of this video. Hope you enjoyed it.